can join afterwards. Okay, first of all, you should give your attendances. You just write in the chat box if you are present, and just your name and followed by you are present. All right. So then let us continue. So if you remember our the problem we wanted to focus on yesterday was that you have been given a functional which I denoted by S, that is uh, a definite integral between the parametric values of t1 to t2. And there was a function of a function which I denoted by L. So L is a function of q dot and sometimes t explicitly dt. Okay. Now what we were interested in, we wanted to find the path for which this L is an extremum. I mean, we want it to be minimum, but let's for now let's say it's an extremum. So suppose this is your t-axis, this is your q-axis, and you had 2 points, pre-given points. So this one I denoted by q1 t1, and this was denoted as a q2 t2. All right. So there were many paths possible. I said that the correct path be this one. So I denoted it by q0t. And suppose there are other possible routes that the system can follow. Let's say this is another one of them that I denoted by say q at any arbitrary path. So then our goal is to find that how to find q0t for which this S is an extremum. Okay. So this is the this is our goal. Now you can obviously see that there are so many paths possible. How do I even try to capture those effects in a neat mathematical manner? As it appears, there is one way of doing the things. So if you just parameterize the any arbitrary path as a perturbation, as a deviation from the correct path. So the thing is, what I want to do is that uh, parameterize uh, an arbitrary path as a deviation from the say correct path, which I have denoted by q0t. So in a sense, what I mean is that, so if you are given any arbitrary path qt, so this qt I will denote it as q0t plus alpha. This alpha is a parameter, okay, like it's a number, alpha times eta t. Okay, so this eta t is an arbitrary function of t. This is an uh, arbitrary function of t. Okay, and of course this q0t is the correct path. Okay, so and this alpha is a parameter that parameterizes the deviation. Okay, so this alpha basically parameterizes the deviation from q0. All right. So now, if this is the structure of my path, if I parameterize my path in this way, this qt is just q0t plus this thing, then my this quantity S, this S will now be a function of alpha. Okay? Because this Q depends on alpha, so does Q dot. So S will be a function of alpha. So now this S becomes a function of alpha. So for every value of alpha, you choose an eta t. You choose an eta t. Suppose eta t is equals t square, let's say. Okay, and you choose a value of eta t, and then for every possible q that depends on alpha, the integration will depend on alpha. But one thing remains true: at alpha equals 0, you are led to the correct path q0t. So at alpha equals 0, S will be, let's say, minimum. Okay. So if you plot S against alpha, then the plot will look something like this. Suppose these are your axis. Suppose this is my alpha, and this here I plot S alpha. Then this plot will look like this. So this is my alpha equals 0, right? So this is my alpha equals 0. This is the origin. Okay. So the this will be this. So here I have chosen a particular value of eta t. Of course, this plot will depend on what value of eta t do you choose. So suppose here you choose eta t equals t square. Now you might ask, what happens if I choose a different eta t? Suppose I choose eta t equals t cube. Okay, that's fine. You will have a different structure of S alpha, but the truth remains that at alpha equals 0, you are led to Q0t. So at alpha equals 0, you will always have the extremum of S. Okay. So if you choose eta t equals t cube, you will have a kind of a different thing. Let's say like this. I'm drawing it super nicely. So suppose this is eta t equals t cube. Okay. So different choices of eta t will give you different a different structure for this curve, if I might say. But the truth remains that for all possible choices of eta t, at alpha equals 0, you will have the minimum of S. Okay. So without any ambiguity, you can always write that if Q0t is my correct path, then ds d alpha at alpha equals 0 should be 0. Okay. So this is my the governing principle. Okay. Does everybody understand that? Let me know if there is any confusion up until this point. Okay. Yes, one by one. Tell me.
Yes, sir. One thing I can understand here that S is a function of alpha, right? When we parameterize Qt as Q naught plus alpha eta. But there is an integration over the L function, which is a function of t.
Yes.
So
you are integrating
so
over t, but you are not integrating alpha. So if
no,
that's why S turns out to be a function of alpha.
Yes, but it should be a constant into alpha.
No, I mean that is still a function of alpha. I am not specifying what kind of function S is of alpha. S depends on alpha. If you input a value of alpha and you get a different value of S. For alpha equals 2, you get a value of S. For alpha equals 3, you get another value of S. Okay, and you basically plot that. Okay. So I am not specifying what kind of function S is of alpha. I do not know that.
Okay.
Okay. If you are not satisfied, you can continue. Not an issue. You can try to explain again.
Actually, in the graph you have drawn that S alpha versus alpha.
Yes.
Where you have drawn a graph like parabola, a shifted parabola. which you
It's not a
denoted as
parabola. It can be anything other stupid graph. I mean,
yes, but
the thing is that at alpha equals 0, this S has an extremum. That's the thing.
okay.
Okay. There is no, I mean, the only feature you should take from here is that at alpha equals 0, the S has an extremum. Okay. It
No,
could be,
actually, my question
yeah, tell me.
is that in the graph of S alpha versus alpha, how it depends on the nature of the curve theta t.
How it depends on the eta t,
Yes,
because
because
it,
it's integrated over t. Then
right?
we get S.
Yes,
Yes.
but what kind of function of qt is, so the integration will depend on that, right? So if you are integrating t square or t cube, your result will be different, right?
Okay.
Right. If you are integrate, if you choose eta t to be t square, you will have a different integration. You choose eta t equals t cube, you will have a different value of the integration. But the things will not matter at alpha equals 0, because at alpha equals to 0, the
Yes.
eta t dependence drops out. That's why they coincide at alpha equals to 0, and everywhere else, to keep things general, they will not coincide. That's why I drew this graph the way I did.
Okay, sir.
Okay. Okay. There was another question.
So there must be a function on the arbitrary function of t, right? Eta
Eta
t.
t is an arbitrary function of t. It will have a boundary condition, but carry on. Tell me. Let me first hear your question.
Because so we have put it in the function as a replacement of qt, right? We have defined qt in terms of eta t and some constant and q naught t, right?
Yeah.
So then in the function L, we have also q dot t, which is basically the first derivative. So like neta t must always be defined, like it should always be differentiable, right? We cannot like choose any random
Yes,
function.
yes, yes. I mean, when I talk about path, I always imply that it will have continuous derivative of all order. I mean, it's Taylor expandable. Yeah,
Okay.
that is, and it will. I mean, it will also pass through these two paths and these 2 points also. So, I mean, eta t is arbitrary as long as it passes through these two endpoints, because these two endpoints are fixed. I want the evolution from q1 t1 to q2 t2.
Yes, sir. Okay, sir.
Okay. So, all right. So then ds d alpha at alpha equals 0, uh, that should be equals to 0. Now, so then what does it mean to calculate ds d alpha? Because sorry, s is an integral of a function called L. Okay, and this L depends on t also. But remember, when I am taking the derivative with respect to alpha, then the t dependence has dropped out because I have already integrated over t. Okay, so after doing the integration, I am taking the differentiation. Okay, so that is one thing to keep in mind. And now, another thing this eta t should satisfy is that uh, you know at these endpoints the deviation should be 0, because q0t already passes through these 2 points. So eta t should be such that say eta at t1 equals eta at t2 equals 0. So because my endpoints are fixed, because my system must pass through the endpoints, and since q0 already q0 t1 equals q1 and q0 t2 equals q2, so my eta t1 and eta t2 must vanish at these boundary points. Okay, so eta t is arbitrary, like arbitrarily smooth function, uh, but it must vanish at the boundaries. Okay, because my system must pass through those 2 points. So under these two conditions, I have to find out then what should be my condition such that uh, what should be the condition on L such that ds d alpha equals 0. All right. So if I calculate ds d alpha equals 0, so if I can write, let me first write it. So ds d alpha, I am evaluating it at alpha equals 0. So even if I don't say it, just remember that what I mean is that it's evaluated at alpha equals 0. So I can write it as del L del alpha dt, okay, T1 to T2. Remember, S was L dt. Now this L depended on Q dot and T. Now this Q and Q dot has implicit dependence on alpha, the way I have parameterized. Okay. So the Q and Q dot implicitly depend on alpha. Okay. But well, t is an explicit variable, so I do not want to differentiate with respect to t, because on the left hand side, when I take the differentiation, the integration over t has already been carried out. So to capture that effect, when I take the this derivative operator inside the integration, I am doing the derivative with the fact in mind that I will not differentiate with respect to t. I am only differentiating with respect to alpha. So I am only considering the alpha dependence here. Okay. So this ds d alpha, which I mean, I should write it as, first of all, I should write it as dd alpha of integration t1 to t2 L dt. But when you try to put the operator inside, you just keep in mind that you will only take the derivative with respect to alpha and not with respect to t. That's why I changed the differential symbol from total derivative to a partial derivative to keep us us reminding that I will not differentiate with respect to t, because the t dependence has already dropped out. Okay. So now my job is then to calculate this del L del alpha at alpha equals 0. So what I am dropping here implicitly is that I am evaluating everything at alpha equals to 0. That means I am evaluating everything along Q0. Okay. So so now del L del alpha. Okay. So remember, L is a function of Q dot and T. So first of all, you will have del L del Q times del Q del alpha using the chain rule of derivative, and then del L del Q dot and del Q dot del alpha. Now, if you notice carefully, since let me remind you here. So since Q was Q0 plus alpha eta, then Q dot would be Q0 dot plus alpha eta dot, let's say. So then del Q del alpha would be eta, and del Q dot del alpha would be eta dot. Okay. So let me plug these two things in here. So I can write del L del alpha equals del L del Q eta plus del L del Q dot eta dot. Okay. So remember all these derivatives. So since I am evaluating these at alpha equals to 0, then this del L del Q is being evaluated along Q equals Q0. Okay. So this is also being evaluated along Q equals Q0. Okay. So I am evaluating these derivatives along the correct path. So since I am doing everything at alpha equals 0. All right. So then now you plug in this in the integral structure, inside the integration structure. Then you have t1 to t2. So del L del alpha you have just evaluated, del L del Q eta plus del L del Q dot eta dot. Okay. And dt. Okay. Now you put a particular focus on the second term. So this, so I extract out this term over here. So I will evaluate this one. So t1 to t2 del L del q dot eta dot dt. So this is the product rule of integration. So you have the first function unchanged, and then you integrate over the second. So integration of eta dot is basically eta, and you put the boundary condition t1 to t2. So evaluate it t1 to t2, okay, and minus integration t1 to t2. So d dt of del L del q dot times eta times dt. All right. Now, first thing you should notice that this boundary terms vanishes, because so this is 0 because eta at t1 and eta at t2 are both 0. Okay? Because my system should pass through the endpoints. It should pass through q1 t1 and q2 t2. So that's why the boundary term drops out. Okay. And only the second term survives. So I am left with this integration being equal to t1 t2 d dt of del L del q dot times eta dt. Okay. Now you plug this in here. So remember here, if we plug this in, and both has a factor of eta, so I take the factor of eta outside. So then this integration will become integration t1 to t2 del L del q minus d dt of del L del q dot times eta dt. Now this, according to my assumption, ds d alpha equals 0 should be equals to 0, okay, because that is the thing. So remember, so this ds d alpha is del L del alpha dt, so this should be equals 0. Because I want an extremum for that. So this would be equals to 0. Now you have to keep reminding yourself that this eta t is an arbitrary function of t. So this is an arbitrary function of t. Okay. Now the condition that this integral will vanish for any arbitrary eta. Now you think yourself. So suppose you are lucky and you choose a eta such that, suppose eta equals t square minus t cube. Okay. So for that particular choice of eta, this integral may vanish accidentally. Okay. But that's not the case we want. We want this integral to vanish for any arbitrary choice of eta. Okay. So the only way that can happen is that the factor multiplying it is 0. So the only way this integral can vanish for any arbitrary choice of eta t, any arbitrary well-behaved choice of eta t, is that this thing in the inside the bracket is already 0. So I can write it as like del L del q minus d dt of del L del q dot equals 0. Remember, all these derivatives were performed along the correct path, because along which, so these are all evaluated along q0. So now the answer to your question that how to find the correct path such that this s is a minimum or a maximum or a constant, whatever, along q0t, is that if s is defined as s equals L dt, then the correct path is such that if you calculate these combinations of derivatives along the correct path, and this combination of derivative is 0, then that path will give you the correct path. Okay. Or so, and since that describes the evolution of the system along this path. Okay, so the kind of system moves along this path with t. Okay, that's why we call it the equation of motion for the system from q1 t1 to q2 t2. So this is the equation of motion, is sometimes called the Euler-Lagrange equation, or simply the Lagrange equation. of motion. So this guides the evolution of the system from initial point q1 t1 to q2 t2, and just a nomenclature, this s is called the action, okay, and this l is called the Lagrangian function for the system. Okay, so so these are just some nomenclatures, okay, that will be handy in our way. Again, I will pause at this moment, but perhaps I've gone a bit too fast, so you can ask me if anything is unclear here.
Sir,
Yes.
so in the graph of q versus t, and in the graph of q versus t, we have chosen a path. We have assumed the correct path, right?
Yes.
And in the action that is s, we have assumed that the L is a function of the q dot t. So is it possible that, like, it can be some other derivative of q2, like if we are using q dot t here, it can be q double dot t or triple dot, something like that.
It is possible to have L as a function of Q double dot and Q triple dot T, but the physical interpretation of such systems is very convoluted, or sometimes it is not possible to give physical description of such system, like what this means, like why Q double dot. So if you include Q double dot in your, I mean, there is a study of what happens if L is a function of Q double dot or Q triple dot, like higher derivatives of Q also. But the physical interpretation of these uh, are not very straightforward. Let me say that it should be a function of Q dot. That much I can tell you, because to describe dynamics, it should be a function of Q dot. If it is not a function of Q dot, if it's just a function of Q and T, not of Q dot, then you can see that this term is zero. Okay, then the Lagrange's equation reduces to just del L del Q equals zero. Okay.
Okay, sir.
Now, del L del Q equals zero. If you remember, so L contains, from hindsight, I am telling you, L contains T minus V, right? Since there is no Q dot, there is no T here, so only V is there. So you are basically suggesting that del V del Q equals zero. That's the condition for static equilibrium. Okay. So
Okay.
when del V del X equals zero, so either the maximum of the potential or the minimum of the potential or the constant potential. So either you have a stable equilibrium or an unstable equilibrium, or kind of a what is the neutral equilibrium or something like that. So that is statics. So that is not describing dynamics. Okay. There is no motion of the system involved if it is not a function of Q dot. Okay. So that describes your statics. Okay. So for dynamical system, it should it should be a function of velocity. That's why we have Q dot in there. And in general, it can be acted upon by a force, and that's why the Q dependence is there. Okay. And the force might be dissipative, and that's why the explicit dependence on T is there also. So the vast majority of systems that we deal with are basically a combination of these three things, and that's why for physical system we assume that L to be a function of Q dot and T. So uh, you are correct in saying that as far as the general variational principle goes, there is no compulsion to restrict the function inside, like what I call L here, to restrict it to the first derivative of Q. Okay, so the general variational principle transcends beyond that. But for systems of physical interest, we only consider the functions which depends on Q dot and T. Does that answer your question?
Yes, sir.
Okay. Anything else?
Sir, the function eta t can be different in any time. Means what I trying to say is that eta at t1 is some function and eta at t2 is some other function. Can then, if we apply this, then this condition also holds?
No, no, no. See, eta t is a function of t. You have taken that. You have already decided your mind when you are doing something. Suppose you want to draw this white curve here. Okay, then you have already decided that eta t to be equals t square. You already have that.
Yes, sir.
Now, the condition you have is that eta t must vanish at t
At
equals
boundaries.
t1 at t equals t2. So the function you choose for eta t, so if you plot eta t, so if I plot it here, t and there is kind of eta t, okay. So what you do is that you shift the origin in a way such that, I don't know how does this look, y equals x square or maybe this. So remember, so this is my T2 and this is my T1. So eta t should be such that although eta t has a major t square dependence, so this is kind of a t square curve. I should not say eta t equals t square. I should say eta t goes as t square. But it is vanishing at T1 at T2. So this is the structure of eta t that you have taken. Okay.
Okay, sir. No, sir, my point is that in between 2 times T1 and T2, can eta t changes its functional form, but the boundary condition remains same?
Yes, of course. I mean, there are so basically what so you see
No, sir.
here.
Suppose in between T1 and T2, I am choosing 2 points. Suppose T3 and T4. Eta at T3 is some other function, and eta at T4 is some other function. Then
Yes.
also this condition holds.
Yes, of course. So what you are suggesting, see in this figure. So at so you have 2 points. At T1 eta t equals 0, at T2 eta t equals 0. Now that doesn't tell you how eta t should be in between. So eta t can be like this, or eta t can be like this. That's what I mean. So these are all different eta t's. So the only condition that should hold is that at the end point, eta t should vanish. The two specific values of T1, like two specific values of T, one is denoted by T1, another is denoted by T2. At those 2 points, eta t should be 0. That's the only condition I demand, and apart from eta t is a well-behaved function, that's the only conditions I demand, and other than that, there is no other imposition on eta t. Okay,
Okay,
and
sir.
that does not uniquely fix eta t.
Okay, sir.
Okay.
Hmm.
Anything else? All right. So
Sir,
yeah.
so that graph of S versus alpha doesn't depend on the eta t, right? That can be anything, any function of alpha,
I
and it
mean,
depends on the structure of L,
it
right?
depends on the structure of L, that is true, but it also depends on the choice of eta t, because the eta t tells you what function you are integrating. Okay. So you just take two possible examples. I mean, you choose something for L that is a function of Q dot. Let me take the simplest example. Suppose LQ equals just Q dot square. Okay. Sorry, L is just Q dot square. All right. Now, of course, S is integration L dt, right? Now, you have chosen Qt to be Q0t plus alpha eta t. As I said, choose for once alpha t equals t
Yes.
square, and another case t equals t cube or anything else that satisfies the boundary condition. Then you see the functional form of this q dot square that changes itself. So this integration changes. So it depends on what you choose for qt. So in one case, you would be integrating say q0 dot plus alpha say 2t whole square, because the derivative of t square is 2t. That is, and in another case, let me put it a different color. You would be integration. You would be doing integration of q dot plus alpha into 3t square whole square dt. Okay. So these two integration will be different, right? So although the Lagrangian is the same, since you have chosen eta t to be different, your value of s is different. Okay, is different for alpha.
Yes, sir, but sir, here s, both s, in the case of the t square and tq,
Yes.
yes, then 2t and 3t square, the
Yes.
integrated value will change from t square to t cube, but it still depends on the alpha square or alpha.
I don't understand.
Means form remains same. Means q dot, q naught dot square plus
It has a complicated dependence on alpha. I do not understand what you mean by that. It has a complicated dependence on alpha. I have never specified the dependence on alpha. I said that it depends on alpha.
alpha does not vary with the time.
Alpha doesn't vary with time. Alpha is a parameter.
Then if I square this term q dot plus alpha 3t square whole square, then
Yeah.
we will get that q naught dot square plus 2 alpha q naught dot into 3t square plus 9t to the power 4 alpha square. Then
Okay.
the uh, t terms will be integrated from t1 to t2 and the alpha terms will remain and the s will be the function of alpha, but this value will change from t square to t cube, but the dependence of s on alpha doesn't vary there, right sir? I am
Uh,
really questioning about this point.
I mean, this particular feature you were talking about, it only true for this simple form of q dot
Yes
square.
sir, yes, it depends on
Then
the Lagrangian form, but how it can depends on the eta t, because eta is a function of t only and it's integrated from t1 to t2 when it's substituted in the L.
okay, I still don't get it. I have just said that at alpha equals 0, your S is minimum. That's the only thing
Yes,
and there is nothing else. I mean, I am not saying that. So these two, this green plot and the blue plot would be different. Do you agree with that?
yes, yes,
This
yes,
that's the only thing I'm saying. I'm just saying that for different choices of eta t, this S alpha will be different. Do you call it different or do you call it the same dependence of alpha? It's just a matter of tautology. It's just, do you call 2 alpha plus 3 alpha square and 5 alpha minus 6
yes,
alpha square? For me, these are two different functions of alpha.
yes.
Now what you call them is up to you. How do you name them? But these are two different functions of alpha.
Okay, sir, understood. Okay, sir, understood.
Okay.
Okay.
Okay. Anything else? All right.
Sir,
Yes. Yes.
sir, can you please give an example of this from this problem? How could we handle using this formula? And please give an example, sir.
Oh, I will be coming to that. There will be examples. Now things are just abstract, from just up until this point, what I have done is that there is a abstract mathematical construct, what I call action, that is just a definite time integral of a function that I call L that has no physical meaning yet. Okay, just a function, and I am interested in this abstract mathematical problem that I want to find the evolution of a system that is described by this L from Q1 T1 to Q2 T2, and I try to formulate how this system will evolve with time. That's the only thing I have told you yet. Okay, nothing else. But I would be coming to example, if not in today's class, but in tomorrow's class. So keep your patience. If you don't get your answer by tomorrow's class, then do ask me again. Okay.
Okay, sir. Thank you.
All right. Now, the next thing I would like to discuss is that whether this Lagrangian is unique. Okay. So uniqueness of the okay. Now remember that given a function L, there there is a particular condition for which this S will be an extremum along a certain path, and the condition was, I am writing the equation in reverse, so d dt of del L del Q dot minus del L del Q equals 0. All right. Now, so this is what happens. Now, the question I'm trying to ask is that um, suppose, so like S was defined as integration L dt, right, from T1 to T2. And this led me to this equation of motion. Now, I am asking, if I define S prime, another S, let's say, with another function, say L prime dt, T1 to T2, my question is, can I get the same equation of motion? So, in other words, is the definition of L unique, or there is some degree of arbitrariness to that? The answer is there is, and you can prove it directly, which I will give you for a homework. So if you define this L prime equals, so L prime say Q dot T equals L Q dot T plus a total derivative of a function that only depends on Q and T. This doesn't depend on Q dot. So remember that. That is a very important thing. So if L prime is related to L, then L prime and L should give you the same equation of motion. So L prime and L will give you the same equation of motion. All right. Now, so I leave it as a homework for you to check explicitly. Do that, okay? But I can be a bit more clever to convince you that this is indeed true. This is indeed true. So as I said, that if so this was my old action in terms of my L, and suppose this is my new action in terms of L prime. So if I try to do the same variational principle, if try to apply same variational principle in the case of L and L prime, let us try to see what will happen. Okay, so what will happen is this. Okay, so what I have here, let me draw the axis again. Yes, that's good enough. So this was my alpha, and this is, let's say, S or S prime. I would denote later. So for S, I have something like this, right? So this is my S alpha. Now what is S prime? Okay. So S prime is, so let me write down again. So S prime is L prime dt, which is L plus df dt dt. All right. Now again, so integration of L dt plus df dt you can integrate already. So this is f qt from t1 to t2, or like t2 q2 t1 q1. Okay. So because df dt integration is that. Now you remember L dt is the old action, that is S, plus this term, since f only depends on q and t, and that is determined at the endpoint, that is fixed. So this is a constant, that is c. Okay. Remember, q is a constant, not q dot. Okay. So here is here you should think about it. So why I have allowed f to be a function of q and t only and not q dot? Okay. What would happen if we had allowed f to be a function of q dot? Okay. So this is my new action is just my old action plus some constant. So what I have is just this old the new action is just parallelly transported from this S. Okay. So this will be my S prime alpha. Okay. Notice that it does not change the position of the minima. Okay. So the fact still remains that at alpha equals 0, the minimum of S prime is still there. Okay. So this is my alpha equals 0 because this thing does not depend on alpha. So this doesn't depend on alpha because at the boundary there is no dependence on alpha. Okay. Just think about that a bit carefully. That means that at alpha equals 0, I get the minimum for both the action, for the old action as well as the new action. And at alpha equals 0, so whatever is the correct path for S alpha, the correct path for S prime alpha is the same. So it's no wonder that L prime and L will describe the same dynamical system. So what I say that these two descriptions, these are equivalent Lagrangians. So these two Lagrangians are equivalent. So if one Lagrangian differs from the other by the total derivative of a function, and that function only depends on the on q and t. What is this q and what is this t? I will come in the next class. But if it depends on the total derivative of q and t, then those two Lagrangians are equivalent. Okay. So that gives you an important lesson that the Lagrangian for the system, for a dynamical system, is not unique. So if you are trying to describe a system, you always find a Lagrangian, never the Lagrangian. So the Lagrangian, you never find the Lagrangian, you find a Lagrangian. Okay. And that is to say that if somehow you can guess rather one Lagrangian that describes a system, it would be as good as any other. You do not need to find any more. So sometimes you are under the impression that given an equation of motion, I can uniquely find the Lagrangian, and Lagrangian is just t minus v always. That's not correct. Okay. So there is no one correct Lagrangian. There are, in theory, there are infinitely many correct Lagrangians, and the Lagrangian will not always have to conform to your naive expectation that it would be t minus v. In some special cases, you can choose the Lagrangian to be t minus v. I will come to that point later. But in a general scenario, I would describe what kind of generality will be there. The Lagrangian is not bound to be t minus v, and actually a Lagrangian is not bound to be anything. It's just for now, a Lagrangian is just a mathematical tool that gives you the correct equation of motion, and there is no unique way of choosing a Lagrangian. We choose the Lagrangian that is most convenient to work with, and that has the property of minimality, and it is more directly evident from symmetry, etc. But other than that, there is no unique choice for a Lagrangian. All right, perhaps I have completed my quota for today's class, so I will stop today's class here. Maybe a couple of quick questions before you leave, and then I will close the session. So tell me if you have any questions here.
Hello, sir.
Yeah.
So suppose I write the Lagrangian in the form of t minus v, and I figure out that there are some total derivatives which are just function of q and t. Then we can separate those out, and
Yeah, you can just drop those. Yeah.
yes, sir. Okay, sir.
Anything else? All right. So if not, then let me stop recording now. All right.